this chapter, we're going to study different statistical distributions. In this lesson, we're going to be looking at binomial distributions.
Okay, hi everybody. So now we want to take a look at binomial distributions. And to introduce this idea, what we're going to do is we're going to go through an experiment here that would be considered like a binomial sort of an experiment. And we're going to try to draw out the ideas before we specifically outline what they are. So, for example, a penny, a dime, and a quarter are flipped at the same time. We're going to complete the table by listing all the possible outcomes of the three coins. Now, and bear in mind that there's only two outcomes for each coin, okay? It's either heads or tails. So here we go. So for a penny, it could be heads. For the dime, it could be heads. For the quarter, it could be heads. Then we could have a heads, and a tail. The quarter could have come out as tails here. Or penny could still come out as heads. This could have been a tails, and this could have been a heads. Penny could have come out as heads. This could have been a tails, and this could have been a tails. Okay, so the quarters. Then we come over here. Now we're going to look at the possibilities where the penny comes up as tails. That would be heads, that would be heads. And then we're just going to follow the pattern that we've established up there, where the quarter keeps flipping back and forth. And once the quarter's gone through both of its options here, the dime will switch to its other option. And then we'll go back to heads, and this will be tails, tails, tails. So here are all the possible outcomes of this little experiment, which means this represents what we call the sample space for this experiment, okay? So the probability of an event, remember, is the set S, the number of successes divided by the number, which is, by the way, the number of favorable outcomes, over the total number of possible outcomes. So right now we can see that there are 8 possible outcomes for this experiment here. Now let's take a look at the specific questions that they're asking. What's the probability that you don't get any heads? So this is basically the probability. This is the probability of T, tails, tails, tails. And we can see that that's 1 out of 8. Okay? There are 8 equally likely results, and one of them is a situation where we get all tails. How about exactly one head? Okay, well, now, hold on a second. Exactly one head. Now, wait a minute. That could be this one right here, where the head was on the quarter. Could be right here, where the head is on the dime, or it could be right here, the head is on the penny. Okay, so there are 3 possible events where that could occur. So exactly, one head. Well, there are 3 out of 8 possibilities where that occurs. How about exactly 2 heads? Well, let's go back up here. Now, there is a kind of a shortcut way of thinking about this, but 2 heads, there's one option right here, there's another option right here, and then there's one right here. So again, there are 3. Okay, exactly 2 heads. It's going to be 3 out of 8. Now, another way of thinking about that is, what's the probability of having exactly 1 tails, which would be the same as the heads there, and exactly 3 heads. So it's going to be head, head, head here. Well, that's just going to be 1 out of 8, okay, because there's only one way that can happen. Now down here, we want to create a bar graph to illustrate what's going on with this sort of thing here. So the bottom here is going to be the number of heads that shows up. I don't know why that's shifted over a little bit. And then the probability. Well, the probability of no heads we saw was 1 out of 8. The probability of 1 heads was 3 out of 8. 2 heads, okay, well, the 2 heads up there was again 3 out of 8. And then 3 heads, so there's only one way that could occur, and that was therefore 1 out of 8. Okay? So there are my probabilities. Now, with that in mind, let's answer another question here. What is the probability of getting at most 1 head? Okay, at most 1 head. Well, at most 1 head means I could get 1 head or I could get none of them. Okay? So this is going to be the probability of getting 1 head or 0 heads. And so we can see that the probability of getting 1 head, that was going to be 3 out of 8. plus 1 out of 8? And the answer is 4 out of 8, or 1/2. Okay? There's a 1/2 probability that I'm going to get at most one head. What's the probability of getting at least one head? Well, at least one head means I'm going to get 1 or 2 or 3. And so the probability of getting one head we just saw here was going to be 3 out of 8. The probability of getting 2 heads, okay, which was really just the probability of getting one tail, was going to be 3 out of 8. And then the probability of getting 3 heads, well, there's only one way that can happen here, and when you put those all together, we're going to get 7/8. Okay, and so there is a kind of just a quick look at a problem that deals with flipping coins, where you've got this, what we call a binary event, right? I mean, it's either a head or it's a tail. Okay, so now we're going to expand on this in a slightly different way. Okay, now our other way of looking at that same problem with the coins there, okay, is going to be to incorporate some combinatorics with it. We're going to use combinations here. So if we take a look at the number of heads here, okay, and let's say it's 0, well, the way that would work here is if you got a tail, tail, tail. So of those 3, I'm going to choose none of them. So I'm going to choose 0 to be equal to heads. Now, how many ways can that occur? Well, just once. So here we go. Now, this is the probability of getting a head on any coin, and I have 0 of them. This is the probability of getting a tail, okay, and there's going to be 3 of those. So then what we do is we multiply the probability, the number of ways of getting, okay, no heads, by the probability of getting no heads, and we get 1/8 there. Now, in that first line explaining it, that really doesn't make a whole lot of sense. Hopefully it'll start to make more sense as we go through it. Now let's take a look at what happens if you've got one head. Well, how many ways can that occur? Well, it could be HTT, THT, or TTH. So of the 3 possibilities, I'm going to choose one of them to be a head. So 3 choose 1 is 3. So this is the number of different ways that can occur. Now, for each one of these, there's one head. Well, the probability of getting a head on a coin is 1/2. This is the probability of not getting a head. If maybe that's a better way of saying it, like getting a tail, but not getting a head. Okay? And there's going to be 2 of those. So now what we do is we multiply the number of ways this event can occur by the probability that each of those events occurs, and we're going to get 3 out of 8. So now let's fill in the next 2 rows here on our own here. If there's going to be 2 heads, well, that could be head, head, tails, head, tails, head, or tails, heads, heads. So of the 3 different ways, or the 3 different letters here that I can choose from, I want to choose 2 of them to be equal to heads, and there are only 3 ways that I can do that. Now, the probability that I get a head is 1/2, and I want that to happen twice. The probability that I don't get a head, or I get a tail there, is going to be 1/2, and I only want that to happen once. So this is the probability of a single one of these events. So now if I multiply 3 choose 2 by 1/2 squared by 1/2, I will once again get 3 out of 8. That's the probability that this event occurs. And now down here, I want to get all 3 are heads. So it's going to look like this. Head, head, head. How many different ways can that happen? Okay, well, of the 3 to choose from, I want all 3 of them to be heads, and there's only one way that that can occur. Over here, the probability of that event, well, the probability of a head is 1/2, and I want 3 of those. The probability of the tail shows up, or it's not a head, is going to be 1/2, and I don't want any of those to the 0. So this will end up being 3 choose 3, 1/2 cubed, multiplied by 1/2 to the 0. And just like above here, and we've already seen this probability, that goes to 1/8. Putting that all together here, okay, here's the formula for the last one. Okay, now basically what this ends up doing here is creating something that looks very, very similar to the formula that you use for the binomial expansion. okay, for finding the separate terms of a binomial expansion here. Now, what we're going to do in the next little section is we're going to kind of put this together and describe to you what's going on in more of a theoretical way, and then we'll apply it again. Okay, so now we're going to talk about this kind of a more of a theoretical sense. So a list of possible outcomes and the associated probabilities is called a distribution. Okay, so as soon as you list kind of all the ways that an experiment can happen and you attach the probabilities to them, that's what we call a distribution here. Now, in this case here, what we're looking at is called a binomial distribution right here. And the reason why it's binomial is because of these little features right here. In any trial, there are only two outcomes. It's either success or failure. So in the example that we were just doing, on a coin, when you flipped it, you either got a head or you didn't. Now, you might look at it as getting a head or a tails, but actually, the way we want to interpret that is we want to look at the probability of an event occurring or not occurring, okay? We don't want to kind of give it another option there because people tend to get confused by that. Because if you say, like, what's the probability of, for example, your favorite hockey team winning, the exact opposite of that is not losing, because there is the probability of a tie in there. So not all events are kind of this easy to demark here. But in this case here, success or failure, in the previous example, it's either we got a head on the coin or we didn't. Each trial is independent, meaning that once, if you flip one coin, it doesn't affect the outcome on another coin. And the probability of each trial remains the same. Every time you flip the coin, the probability is a half that it's going to come up as heads. Okay, that doesn't change over time. There's nothing that influences that. It's just, that's the way that goes. So the formula for calculating the probability of k successes in a binomial distribution. So if you're going to apply the experiment n times and you know that the probability is p, okay, of success every single time, and you're looking for k successes, then this is how you do it. Of the n trials here, let's zoom in on this. Okay, of the n trials, I'm going to choose k of them to be successes. The probability of a successful trial will be p, and I want that to happen to k times. And then I'm expecting that I'm going to have failure n minus k times. Okay, so just think about it with the other example here. I had 3 coins. Let's say I wanted to get 2 heads. So it's 3 choose 2. The probability that I get a head is a half, and I wanted that to happen twice. The probability that I get a tails was 1 minus a half, or a half. And I only wanted that to happen once. Okay, that's what this particular formula is doing. Okay, now, because we've got these graphic display calculators, most of us have got these calculators here that have got some preloaded programs on them, we can actually kind of expedite that work a little bit here because the calculator has that in this feature in its memory. So if you want to find the probability of exactly k successes, we're going to use a function called the binomial PDF. Okay, so it's in the same spot that we found the normal CDF and the inverse norm, binomial PDF. And the syntax here, and I'm going to zoom in on this one. Whoops, wrong way. I'm going to zoom in on this one again. Is you enter in the binomial PDF. So it's binom PDF. The number of trials is n. The probability of success is p, and then the number of successes that I'm looking for would be k. So binomial PDF npk with commas in between. Okay, now find the probability of at most k successes. So now this is from 0 up to k successes. And it's really important that you catch that because a lot of times when I have students that have struggled to get this answer correct, it's because they're not actually doing at most, they're doing at least. And you're just going to have to pay very close attention to the question and the work that you're doing to make sure that makes sense. The calculator has a feature for doing that. It's the binomial CDF, the binomial cumulative distribution function. And so you find it in exactly the same spot as we were looking before. So let's zero in on this here. So here's the syntax. It's the binomial CDF. It's the number of trials, n, the probability of success, p again. But now you just put K there. Now, the only difference between this and what we just did up here is that this is CDF, not PDF. And so what this does here is this takes K. K takes on values from 0, 1, 2, up to whatever number you plugged in there. And then what the calculator does is it figures out what the solution is at 0, at 1, at 2, at 3, at 4, blah, 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 up to this unknown number, and then adds those all up. So, but it goes, again, it goes back to 0 and works up to that value right there. Now, the last one here that we want to look at here is the probability of at least K successes. So that this means from K to N. Okay, so whatever value of K is, all the way up to every event being a successful event. This one, again, we're going to use the binomial CDF, but we're going to do this a little bit different. We're going to be sneaky about this one. To do the at least, what we're going to do is we're going to use 100%, and we're going to subtract the exact opposite. We're going to subtract at most K minus 1 successes. And this right here, this is the part that people struggle with, okay? This K minus 1. Because if I want to know what's the probability, for example, that I get at least 2 heads, the exact opposite of that isn't at most 2 heads. And if you just think about those two different scenarios here, at least 2 heads, at most 2 heads, they are not exact opposites of each other because they both include the probability of getting 2 heads. From 2 heads up, from 2 heads down low. Well, that's not the exact opposite here. So what I need to do here, if I want the probability of getting at least 2 heads, then I have to subtract the probability of getting at most 1 head from 100%, and I subtract the exact opposite. So it would be like me taking, let's say 20, if I say 20 free throws. Okay, so I've got my basketball. I'm going to make 20 free throws, and let's say I know that my probability of success is, well, let's be honest, let's say I'm 1/5. Only 20% of the time am I going to make it here. And I want to know what's the probability of me getting at least, let's say, 10 throws. Well, what I'm going to do is I'm going to take 100% and I'm going to subtract the exact opposite of this. And this is going to be the binomial CDF. Okay, I'm going to make 20 shots. So N is the number of shots that are going to be made here. The probability of success is 1/5. But now, the exact opposite of at least 10 throws is at most 9. Okay, so the probability of me making at least 10 throws is 1 minus the probability of me making at most or only up to 9 shots. I hope that makes sense. Now we're going to take a look at some problems to go along with that. Okay, let's take a look through this problem right here. It says a fair die is rolled 4 times. Okay, so I know that the N is going to be 4. That's the number of events. What's the probability of rolling the number 5 exactly once? Okay, well, the probability of getting the 5 is going to be 1/6. And in this case here, I'm only interested in it happening once. So this is going to be the binomial PDF for 1/6 and then 1. Okay? And let's go through and take a look at what that's going to look like. So second vars, okay, to get us into this menu right here, and I'm going to go down to the binomial PDF down here. I'm going to have 4 trials. The probability of success is 1/6, and the number of successes is just going to be 1. And that writes it out like I have it written here. And when I press enter, I'm going to get okay, let's go to the nearest hundredth, 0.39. So approximately 0.39. Now, what is the probability of rolling the number 5 at most once? Well, for at most once, that's going to be the binomial CDF. This is exactly what the binomial CDF function does. Okay, so 4 trials, 1/6, and 1 here. Now, what that's going to do is that's going to start with this being equal to 0, figure that out, evaluate it, then at 1, figure that out, and add those together. So now I just got to basically just change the function that I used here. So second vars, we're going to go down to the binomial CDF, 4 trials, 1/6, and 1. Looks the same, except for that one letter there. And now I'm going to get 0.87. Okay, so approximately 0.87. And now, what is the probability of rolling the number 5 at least twice? Okay, at least twice. So now to figure this out at least twice here, because it's at least, okay, I'm going to use my 1 minus my at most function, which is the binomial CDF, but at least twice, the opposite is going to be minus at most once. So I've already got that work on my calculator here. So now all I'm going to do here is I'm just going to do 1 minus the work that I just did. And we're going to get to the nearest tenth, nearest hundredth, 0.13. 0.13. And that would be the probability of getting the number 5 at least twice. Okay, so this question here says a multiple choice test has 10 questions, each with 4 options. Ralph randomly guesses the answers to each question. Uh-oh, randomly guessing here. So 10 questions. That means the number of trials is 10. And if there's 4 options for each one, we know that the probability of guessing each one correct is going to be 1/4. Okay? So let's take a look at the questions here. What is the probability that Ralph answers exactly 4 questions correctly? Well, because it's exactly, this is going to be a binomial. Okay, binomial PDF. 10 trials, 1/4, and then 4. Okay, because in this case here, remember our K, the number of successes is going to be 4. So now, we just go to the calculator. So second vars to get into the distribution menu, we come down, binomial PDF, 10 trials, 1/4 probability for each one, and I want 4 successes. So to the nearest hundredth, it's going to be 0.15. Okay, so this is approximately 0.15. Now, what is the probability that Ralph answers at most 4 questions correctly? Well, okay, that is our binomial CDF problem. And it looks the same. Okay, so it's just a matter of changing that function to a binomial CDF. Still 10 trials, probability is still 1/4, and this time we're still looking for 4 successes, at most 4 successes. So what that's going to do is going to make that 0, 1, 2, 3, and 4, evaluate them separately, then add them up. Ooh, and we get 0.92. Okay, so there is a 0.92 probability that he's going to get at most 4 questions correct, so somewhere between 0 and 4. Now, what is the probability Ralph answers at least 5 questions correctly? Okay, so this is important. For those of you that believe that by randomly guessing you give yourself a shot at doing well. Well, this is going to be 1 minus the exact opposite of that, which is the binomial CDF. At least 5 questions. The exact opposite of that is at most 4, which is what we just did. And so I've already got that number in here, so all I got to do is 1 minus that result there. Ooh, and we get 0.08. Okay, so not good. Okay, not a really good probability that by randomly guessing, and it's just a 10-question quiz, right? Not very good odds at all. Okay, so here's our third example here. It says, in baseball, a batting average is the ratio of hits to the times at bat. Okay, so in modern times, a season batting average higher than 0.3 is considered to be good, and an average higher than 0.4 is nearly unachievable. And then to give you a little bit of information here. So Ty Cobb holds the record for the highest career batting average at .366. All right, so here's the question. A baseball player has a batting average of 0.3. So that is our probability at this point, 0.300. Find the probability that the player gets at least 4 hits in the next 8 times at bat. So that's n is equal to 8. This is an at least question, so it's going to be 1 minus the binomial CDF, the cumulative distribution, okay, up to, well, it's going to be the opposite of at least 4 hits. So it's going to be 8 times at bat with a probability of 0.300. And the exact opposite of at least 4 is at most 3. And I'm assuming we're going to have to round that. So now, let's go to the calculator. This will be 1 minus the binomial CDF. We've got 8 trials now. The probability is 0.300. And this time, 3 times up to bat, 3 hits. And we get 0.19. Okay? So now look at that. The probability that he gets at least 4 hits in the next 8 is not very good, even though this guy's got what's considered a really good batting average. That's just the way the numbers work.